In this video, we will discuss about the application of Gauss theorem. Here, the first we will discuss about the first application, that is electric field due to infinitely long straight uniformly charged wire. Before we directly go into calculating the electric field, let us first discuss about electric field lines because of infinitely long wire. So here, this is your infinitely long wire and the positive charge is uniformly distributed. To draw an electric field lines for the infinitely long wire, I took a plane which is perpendicular to this wire. Then this plane is perpendicular to the line. Here the electric field lines at this point is radially outward as shown in this diagram. This can be further understood here. If this is infinitely long wire, this is your infinitely long wire, and if I place it along this direction and I took a plane which is this is a plane like this one, then the electric field lines will be along the direction which is shown in this page. So if at each and every point, at this point the electric field lines are this much, for this point electric field lines are this much, for this one, each and every point electric field lines are similar as shown in this plane. Similarly, we can see that the electric field line infinitely long wire is radially outwards. Second point, it has, because of this one, similarly if I draw here also the electric field lines for this particular plane, and this also having a spherical symmetry. If we draw this one, it forms a cylindrical, so it is having a cylindrical symmetry. So from this we understood the two basic properties of electric field lines. It has radially outward and it has cylindrical symmetry. So I took this is your infinitely long wire over which the positive charge is uniformly distributed over this wire having linear charge density lambda. Let P be the point at a perpendicular distance r from this wire where we want to calculate the electric field. I want to calculate the electric field by using Gauss theorem. So here we want to use the Gauss theorem. To apply a Gauss theorem, I should choose a suitable Gaussian surface. As we discussed that it has cylindrical symmetry, so I will draw a cylindrical Gaussian surface. I draw the cylindrical Gaussian surface of radius r and length L. Of radius, we choose a cylindrical Gaussian surface of radius r and length L. Now this cylindrical surface has three kind of surface. I took this as a S1, this surface is S2, and the curved surface, that is S3. See here, if this is your cylindrical surface like this one, so it has two surfaces. One is this one, this is your S1, this is your S2, and this is a curved surface area, this one, the round one. So this is yours three surfaces for the cylinder. Now I will choose this. Now there are three surfaces the surface element of S1 surface is outward, that is along this direction, and the surface element of this S2 surface is also outward, that is along this direction. And the S3 surface have a curved surface, its direction is radially outward, that is along this direction. This is your ds. Now I will apply the Gauss theorem. So says the amount of flux coming out of the closed surface, that is this much, E dot ds, is equal to 1 by epsilon naught the total charge enclosed by the surface. So here I will calculate first what is the total flux coming out of this cylindrical Gaussian surface. So I will start with the left hand side. This is my left hand side and this is my right hand side. So I will start with first left hand side. Now that is flux phi, total flux coming out of this closed cylindrical Gaussian surface, that is E dot ds. Now here cylindrical surface is divided into three parts, so I divide my surface integral into three parts, that is surface S1 E ds, E dot ds, S2 E dot ds. Now I will calculate this E dot ds for three surfaces. So from the diagram, E dot ds for S1 surface. First we see the S1 surface. So this is my S1 surface. Here E dot ds, E, we know that electric field lines for this one is radially outward, that is upward here along this direction. So electric field at this point will be downward along this direction, so which is making an angle of 90 degree. So here E dot ds will be equal to 0, as E dot ds means E ds cos of theta. Here theta is 90 degree, cos 90 is 0. Now the second case for S2 surface. For S2 surface, that is E dot ds, or we say that it is E ds cos of theta, that is equal to, for S2 surface, this is my S2 surface. Here the electric field lines for this surface is along this direction, radially outward. So see here, this angle is also 90 degree. So cos 90 is again 0. So this term is also equal to 0. Now for S3 surface, so E ds is E dot ds vector is equal to E ds cos of theta. Now see here, for S3 surface, this is my S3 surface, curved one surface. Here surface area direction is along this direction, and electric field is also along this direction. Both are in same direction. So angle is 0. So cos 0, 1. So it is E ds for S3 surface. So then our left hand side becomes, this S1 surface is 0. This is second is also 0, plus, and third one is this much, that is E dot ds S3. Now here we know that E dot ds is equal to E ds for three surface. For third surface, then it becomes here E ds for S3 surface. Now further, E is uniform. If you see this surface, cylindrical surface, each and every point of the cylindrical surface, curved cylindrical surface, is equidistant. Surface is equidistant from a line, so E is uniform on the surface. As S3 surface is equidistant from the line, so E is uniform on the surface. So E is uniform, so I can take it outside. So we are left with only ds, that is S3 surface. So here we know that S3 surface is the curved surface area. The curved surface area of a cylinder is given by the total flux coming out of it is equal to E, and integral means total surface area, that is S3. So here for a cylinder, this is cylinder, S3 surface area is this curved surface area. The curved surface area of this cylinder is two pi r L. L is a length of the cylinder. So this is our equation 1. Now the right hand side, from here we can see that the right hand side here is total charge enclosed divided by epsilon naught. Right hand side is total charge enclosed by the Gaussian surface divided by epsilon naught. If you see the figure, the total charge enclosed by this Gaussian surface is equal to the charge contained by the rod which is inside this Gaussian surface. If L is a length of this wire, then the charge on this wire is given by Q equal to lambda into L. So the charge enclosed by this Gaussian surface will be equal to lambda into L. So our right hand side becomes lambda into L divided by epsilon naught. So this is our second equation. From 1 and 2 we get, that is E dot 2 pi r L is equal to lambda L divided by epsilon naught. Now the electric field from here, it becomes is equal to lambda upon L. L get cancelled out, so we are left with 2 pi epsilon naught E into R. So this is your electric field because of infinite line charge. From this diagram we can see that, from this formula we can see that here the electric field is inversely proportional to the distance. So it dies out linearly. As in the case of point charge, the electric field dies out with square of distance. If you draw the graph between electric field and the radius, the graph comes out to be like this one. So this is your E and this is your R, and the graph is like this one.